When you push a single AI coding agent past its limits, the monolithic context structure collapses under the pressure of its own history. Most teams start with vibe coding, using a conversational AI assistant to spin up boilerplate or scaffold a quick feature. In these early sessions, the initial productivity spike is undeniable, but as the project scales, that single conversation becomes a liability. The context window crowds with meta-management, architecture rules, and shifting requirements, leading the agent into hallucinations and circular debugging loops. Modern AI development has reached an inflection point where code generation is abundant, but the judgment required to determine if that code is safe to ship is becoming a scarce resource. Moving past this plateau requires shifting our focus from prompt engineering to repository-native orchestration, treating AI as a system of integrated components rather than a magic text box. To achieve this scale, we rely on three pillars: specialized multi-agent squads, executable harnesses that contain them, and a strict verification loop driven by human oversight. By treating AI implementation as a systems architecture problem, platform teams can scale their workflows without risking the stability of their codebase. Manually pasting tech stack rules and architecture conventions into every new agent prompt is a recipe for context exhaustion before the actual work even begins. We solve this by decoupling project context from the immediate prompt through static memory files, like a claude.md or agents.md file committed to the repository root. This project constitution loads into every new agent session by default. Any agent dropped into the repository is instantly onboarded and bound by the same version-controlled rules. For situational expertise that doesn't need to be in every prompt, we use modular blocks called agent skills. Skills function as progressively disclosed folders containing specific procedural knowledge, like typography standards or query optimization patterns, that activate only when a task requires them. This progressive disclosure preserves the agent's working memory by preventing the context window from bloating with irrelevant documentation. Externalizing memory into files ensures that agent behavior is predictable and auditable across the entire development lifecycle. In an agentic world, passing a standard CI/CD pipeline is no longer proof of safety. A coding agent can generate a flawless-looking pull request that still degrades your infrastructure at scale. To manage this, we use harness engineering, building a closed-loop environment where agents act with high autonomy because their output is continuously verified by external sensors. This matrix categorizes our guardrails. Feed-forward controls steer the agent's intent before coding. Feedback controls provide post-execution signals for self-correction. Computational sensors, like linters, are fast and deterministic, while inferential sensors apply semantic judgment to catch missed edge cases. For these sensors to be effective, they must be shifted left in the pipeline, providing feedback to the agent while it is still in the execution loop. Continuous validation, running load tests and chaos experiments, allows us to stress test the operational assumptions baked into the agent's code. Without this rigor, an agent might optimize for a green unit test, while silently introducing retry logic that causes a thundering herd on a downstream service. The effectiveness of these sensors depends on the ambient affordances of the codebase, the structural properties that make it legible to an agent. Codebases with strict module boundaries and strong typing provide more hooks for automated sensors, making them inherently more harnessable. Safe, autonomous generation is only possible when the infrastructure is rigorous enough to contain the blast radius of inevitable AI errors. Modern orchestration uses a thin coordinator agent. Its role is strictly to route tasks and manage subagents, not to implement code itself. When one agent tries to manage design, implementation, and testing logic simultaneously, the context splitting forces it to make compromises in reasoning. Context replication solves this. We duplicate the shared repository data into several parallel, isolated context windows. The coordinator spawns specialists, one for the backend, one for the front end, and one for testing, each with their own isolated 200,000 token context window. In this sequence, the backend agent drafts the initial logic based on the spec. Then, the isolated tester agent runs its evaluation suite against that draft, operating from a fresh perspective. If the tests fail, we enforce a critical rule. The original agent is locked out of revising its own work. Forcing a separate agent to implement the fix eliminates the confirmation bias inherent in LLMs, requiring the code to survive independent validation before it ever reaches a human. This structural separation of implementation and validation mirrors the security protocols human teams use to prevent shipping bad assumptions. Relying on real-time live chat synchronization between multiple AI agents is too fragile for complex repository work. Instead, we use the Dropbox pattern, moving coordination out of the chat session and into the file system. Agents communicate strictly by appending structured data blocks to a version-controlled Markdown file. This becomes the team's shared brain. This provides a legible audit trail of every architectural choice, giving you a record of the reasoning behind the code. Because this memory is stored in the repository, the AI squad can recover full context and resume work seamlessly after any disconnect or restart. Using versioned files for coordination allows multi-agent squads to stay in sync without the setup costs and retrieval complexity of a centralized vector database. Even in a fully orchestrated system, the human engineer remains the ultimate governor through the plan, execute, verify loop. In the plan phase, you author intentional markdown specifications. This forces the human to define the architecture, preventing the drift associated with pure vibe coding. During execution, the multi-agent squad builds and self-corrects entirely within the confines of your engineered harness. In the verify phase, the human takes ownership of the final pull request. You are the final check on whether the code behavior matches the system's requirements. We distinguish between relying on AI and leveraging it, based on whether the engineer maintains a mental model of the change. Relying means assuming code is safe simply because it passed a test. Leveraging means using agents to iterate rapidly, while you retain complete ownership of the load profiles, risks, and production behavior. The most successful engineers in an agentic future will not be defined by the volume of code they generate, but by the ruthless judgment they apply to the systems they orchestrate.